Hello and welcome to this explainer. Today, we're unpacking an absolutely fascinating and honestly absolutely crucial piece of mathematics that essentially powers modern machine learning. We're going to be talking about a brilliant breakdown titled The Math Behind RMSProp, which was authored by Dr. Jayashree Ravi in June of 2024. So if you've ever found yourself wondering what actually happens under the hood when a neural network optimizes its weights, well, you are definitely in the right place. We're going to look really closely at the exact mathematical equations that fix one of the most frustrating problems in deep learning, and we'll understand the underlying logic that keeps your models from just stalling out.
Right off the bat, let's set the stakes with a really frustrating real-world problem. Imagine you're training a deep neural network. Things are going great, the loss is dropping beautifully, and then it just stops. The model abruptly stalls out. It absolutely refuses to learn anything new. And this happens way before it's actually reached an optimal solution. So why does this happen? Well, the answer usually lies in a phenomenon called a diminishing learning rate. You see, when certain optimization algorithms accumulate historical gradient data, they tend to stuff all of that historical data right into the denominator of their update equation. And over time, that denominator grows so incredibly large that the actual learning step the model tries to take shrinks down to essentially nothing. It's a massive roadblock. But thankfully, there's a really clever mathematical way around it.
So here is our roadmap for today. We'll start with the learning rate problem, then introduce RMSProp, decode the math, walk through the four-step algorithm, and finally wrap up with why RMSProp wins.
Okay, part 1, the learning rate problem and the AdaGrad dilemma. To really get this, we have to talk about AdaGrad. Now, AdaGrad was a genuinely great idea initially, but in our story today, it acts a bit like the villain. As a neural network trains, AdaGrad aggressively accumulates the squared gradients starting from the very beginning of the training process, and it places that massive, ever-growing sum squarely in the denominator of its learning rate update rule. Because it just keeps adding these historical values up without ever letting them decay, that denominator grows infinitely larger. And, just from basic division, when you divide your learning rate by a massive, constantly growing number, your effective step size shrinks drastically. Eventually, that learning rate becomes practically zero. The model literally can't take any more steps, and it stops learning entirely. RMSProp, on the other hand, uses an adaptive approach. It completely prevents this extreme shrinking, keeping the denominator in check and keeping the training process alive and healthy.
Which perfectly brings us to our adaptive solution. Part 2. Enter RMSProp.
RMSProp actually stands for root mean square propagation. As Dr. Ravi's paper outlines so well, it's an adaptive learning rate optimization algorithm. Its whole reason for existing is to deal with that exact problem we just discussed with AdaGrad, ensuring a smooth and stable convergence. The core philosophy here is built on two main pillars, adaptivity and smoothness. But what does adaptivity actually mean when we're talking about the math? Basically, it means RMSProp assigns a different, completely unique effective learning rate to every single parameter or weight in the network, and it bases this entirely on that specific parameter's recent gradient history. By maintaining a moving average of these gradients, rather than that infinitely growing sum we saw before, it ensures the learning rate doesn't diminish too quickly.
Let's get into the gears of this thing. Part 3. Decoding the math and unlocking the variables.
First up is this term e of g squared at time step t. I want you to think of this variable conceptually as the algorithm's shock absorber. Technically speaking, the e here represents the expectation or the exponentially decaying moving average of past squared gradients at that specific time step. But why are we squaring the gradient? Well, by squaring the values, the algorithm effectively removes the sign. Whether it's positive or negative doesn't matter anymore. It's focusing entirely on the raw magnitude of the update. So instead of keeping a rigid, ever-growing tally of every single bump in the road since the start of training, this variable smooths out those gradient magnitudes over time, and that crucially helps in normalizing the steps as the network actually learns.
Next up is the Greek letter rho. This is our decay rate. You can really think of rho as the memory manager for the whole algorithm. It's typically set to a value right around 0.9. Its entire job is to determine how much weight is given to the past squared gradients compared to the current squared gradient. Choosing 0.9 is highly intentional here. It means the algorithm remembers a fairly short, focused window of recent gradients, allowing it to quickly forget the distant past. This is exactly what allows RMSProp to dynamically adapt to shifting loss landscapes during training without being completely weighed down by where it was, say, 10,000 steps ago.
Let's walk through the math to see how that decay rate functions in reality. With rho set at 0.9, the algorithm calculates 0.9 times the history of past gradients. It then adds 0.1, which is just 1 minus rho, times the immediate current gradient. By blending these two together using that specific 90-10 ratio, we get our next update. A perfectly balanced, smoothed-out trajectory that prevents those erratic, wild jumps while still remaining highly responsive to brand-new data.
Okay, our third variable is epsilon, which is the stability constant. This is an incredibly tiny number. We're talking typically around 10 to the negative 8th power. Epsilon is basically our numerical safety net. Think about a scenario where a parameter hits a completely flat gradient area, meaning its gradient literally becomes zero. Since we are eventually going to be dividing by our shock absorber term, a zero gradient could cause a catastrophic divide by zero error, instantly blowing up your entire model with not a number values. So simply adding this tiny epsilon to the denominator ensures the math stays robust and doesn't break no matter how flat that loss landscape gets.
And finally, we have alpha, the learning rate. If our other variables are the shock absorbers and the safety nets, alpha is our global base learning rate. It's the master dial. It dictates the overall baseline of how fast or slow we want the network to adjust. RMSProp's real magic, though, is that it takes this singular global alpha and uses our previous variables to scale it differently for every single parameter in your deep learning model.
All right, let's put it all into practice. Part 4, the 4-step algorithm, putting the engine together.
According to Dr. Ravi's paper, the entire process runs on a continuous 4-step loop. We initialize our parameters, compute the gradient, update our running average, and then update the parameters themselves. It's just a constant, beautiful cycle of calculating, smoothing, and stepping forward. Let's break it down step by step. In step 1, the setup phase, we initialize our starting parameter values, the weights of the network. We set our accumulated squared gradient vector to zeros, and we lock in those hyperparameters, alpha, rho, and epsilon. Then moving to step 2, at each time step, we compute the gradient. Typically found using backpropagation, this represents the partial derivative of the loss function with respect to that specific weight. Put simply, it gives us the exact current slope or trajectory of our data at that precise moment in time.
Now for step 3, and honestly, this is where the mathematical magic really happens. We take that new slope from step 2 and blend it right into the historical moving average. Just to voice the formula clearly, our new expected moving average equals rho times our previous average plus 1 minus rho times the square of our current gradient. Boom! That's our shock absorber activating. Because we are continuously replacing the old average using this exponentially weighted formula, our denominator is never going to grow out of control like it did back in AdaGrad.
Finally, step 4, the parameter update itself. We update the parameter by taking the old parameter and subtracting a very carefully calculated step. That step is our global learning rate, alpha, divided by the square root of our new moving average plus epsilon, all multiplied by the current gradient. Now, why is this division so absolutely critical? Because dividing by a large moving average automatically shrinks the learning rate for wildly oscillating parameters, preventing them from just jumping off a cliff. Conversely, dividing by a small moving average boosts the learning rate for parameters that are moving way too slowly. It's a self-correcting system that automatically normalizes the pace for every single weight in the entire network.
And that brings us to part 5, why RMSProp wins and its advantages.
So what should you really take away from this explainer? Well, directly from the source material, RMSProp offers 3 major practical advantages based on the exact math we just covered. First, it handles non-stationary objectives beautifully. Because the decay rate, rho, aggressively forgets the distant past, the algorithm easily adapts when the underlying data distribution changes over time. Second, it is highly suitable for noisy problems. Because that exponentially weighted moving average acts as a shock absorber, it smooths out the chaotic, noisy gradients that are super common in stochastic optimization. And third, adaptivity. It scales the learning rate individually per parameter, ensuring that every single part of the neural network learns at a perfectly tailored pace.
So let's bring it all back to that frustrated data scientist from the very beginning. By swapping out an infinitely growing denominator for a smartly decaying moving average, RMSProp ensures your model doesn't stall out. It allows for smooth, stable convergence across wildly varying gradients. But it leaves us with a really exciting thought to ponder. As our machine learning models grow exponentially larger and the data distributions they analyze become even more chaotic, how will these adaptive mathematical algorithms evolve next to handle the neural networks of the future? Something to think about. Thank you so much for joining me in this explainer to unpack the math behind RMSProp. Keep exploring, and I'll catch you next time.